The existence of a diamond planet forces us to reconsider not just planetary formation, but the entire concept of geological time and planetary evolution. On Earth, we measure geological epochs by the changes they produce. Mountain ranges rising and eroding, continents drifting across the globe, oceans opening and closing, climates shifting between ice ages and warm periods. These changes leave traces in the rock record, layers upon layers of sediment that tell the story of our planet's dynamic history. But a diamond planet operates under fundamentally different rules. Diamond's exceptional hardness means it resists erosion in ways that ordinary rock cannot. On Earth, water, wind, and ice gradually wear down even the most durable stone. Given enough time, mountains crumble into plains. Coastlines reshape. River valleys deepen. The surface is in constant, if gradual, flux. But diamond withstands these forces with almost complete indifference. Water cannot easily chemically weather it. Windblown particles cannot scratch it significantly. Even impacts from meteorites, which would shatter conventional rock, might only chip or fracture diamond rather than pulverize it. This resistance to change suggests that a diamond planet's surface could preserve features for timescales that dwarf anything possible on Earth. Impact craters billions of years old might remain as sharp and well-defined as the day they formed. Ancient topography, shaped during the planet's earliest epochs, could persist essentially unchanged across the entire age of the solar system. The world would become a geological time capsule, its surface frozen into a configuration determined by its violent youth and never substantially modified afterward. This permanence would make such a planet extraordinarily valuable for studying early planetary processes. On Earth, plate tectonics have recycled most of the original crust. The oldest rocks we find are roughly 4 billion years old, but they are rare exceptions. Most of Earth's surface is far younger, constantly renewed by volcanic activity and tectonic movement. The early history of our planet is largely lost, erased by billions of years of geological activity. But a diamond planet, geologically dead and erosion-resistant, would preserve that early history in pristine detail. Scientists could study impact patterns from the late heavy bombardment, a period roughly 4 billion years ago when the inner solar system was pummeled by countless asteroids and comets. On Earth, almost all evidence of this bombardment has been destroyed. On the Moon, craters remain visible, but the Moon is a small body with limited geological complexity. A diamond planet would offer something in between. A large world with complex early geology, all preserved in crystalline permanence. Every impact, every ancient lava flow, every tectonic feature from the planet's active youth would remain visible. A complete geological record stretching back to planetary formation. The internal structure of such a planet raises equally fascinating questions. Earth has a layered structure, a thin crust, a thick rocky mantle, and a dense metallic core composed primarily of iron and nickel. This layering occurred because Earth was once molten, allowing denser materials to sink toward the center, while lighter materials floated toward the surface. This process, called differentiation, is fundamental to planetary evolution and determines everything from magnetic field generation to volcanic activity. A diamond planet would undergo differentiation as well, but with crucial differences. If the planet formed from carbon-rich material, its core might not be metallic iron. Instead, it could be composed of even denser forms of carbon, compressed under such extreme pressure that the crystalline structure transforms into exotic, high-pressure phases. Scientists have discovered that at pressures exceeding those found anywhere on Earth, carbon can adopt structures even more compact than diamond. These super-dense carbon phases have been produced only in laboratory experiments using diamond anvil cells, devices that compress tiny samples between opposing diamond tips. At planetary core pressures, which can reach millions of atmospheres, carbon might form structures with properties we can barely predict. Some theoretical models suggest metallic carbon, a form where electrons move freely through the crystalline lattice, conducting electricity like metal despite being composed entirely of carbon atoms. If a diamond planet's core contains metallic carbon, it might generate a magnetic field through the same dynamo process that creates Earth's magnetic field, where electrically conducting fluid moving within the planet's interior generates organized magnetic fields that extend into space. A planetary magnetic field serves crucial protective functions. It deflects charged particles from the stellar wind, preventing them from stripping away the atmosphere and bombarding the surface with radiation. Earth's magnetic field has protected our atmosphere for billions of years, allowing liquid water to persist on the surface and life to evolve without being sterilized by cosmic radiation. If a diamond planet possesses a metallic carbon core and generates its own magnetic field, it would enjoy similar protection despite its exotic composition. However, magnetic field generation requires more than just conducting material. It requires motion, convection currents within the core driven by heat escaping from the planet's interior. This is where diamond's exceptional thermal conductivity becomes problematic. On Earth, heat flows slowly through the rocky mantle, maintaining a temperature gradient that drives convection both in the mantle and in the molten outer core. These convective movements power the geodynamo that generates our magnetic field. But diamond conducts heat roughly 5 times better than ordinary rock. Heat would escape from a diamond planet's interior far more efficiently, potentially cooling the core too quickly to sustain convection. A rapidly cooling core would solidify, shutting down any magnetic dynamo and leaving the planet without magnetic protection. This might explain why the diamond planet Webb observed shows no signs of a substantial atmosphere in the preliminary data. Without a magnetic field, stellar wind would gradually strip away any gases, molecule by molecule, until the planet became airless and exposed. The same crystalline structure that makes the planet durable and unchanging might also render it vulnerable to atmospheric loss. Yet even this scenario contains subtleties. If the planet formed far from its star and later migrated inward, it might have started with a thick primordial atmosphere, rich in hydrogen and helium captured from the protoplanetary disk. Such an atmosphere, if massive enough, could resist stellar wind erosion for billions of years even without magnetic protection. Gas giants like Jupiter have no solid surface and generate magnetic fields through metallic hydrogen in their interiors, but their atmospheres are so massive that stellar wind cannot meaningfully erode them. A diamond planet with a sufficiently thick atmosphere might retain it through sheer mass, regardless of magnetic field strength. The question of atmospheric composition on a carbon-rich world introduces another layer of complexity. Earth's atmosphere is dominated by nitrogen and oxygen, with trace amounts of argon, carbon dioxide, and water vapor. This composition reflects billions of years of geological and biological activity. Oxygen, in particular, is a biological product created by photosynthetic organisms and maintained at current levels only through continuous biological activity. A lifeless Earth would have an atmosphere dominated by carbon dioxide and nitrogen, similar to Venus or Mars. On a diamond planet, the initial atmosphere would depend on what volatile compounds were present during formation. In a carbon-rich, oxygen-poor environment, methane might dominate instead of carbon dioxide. Methane is a simple hydrocarbon, one carbon atom bonded to 4 hydrogen atoms, and it forms readily when carbon and hydrogen are available. The early Earth had significant methane in its atmosphere before oxygen-producing life evolved. A diamond planet might retain a methane-rich atmosphere indefinitely if no biological or geological processes remove it. Methane atmospheres have distinct optical properties. Methane absorbs red light strongly, which is why gas giants like Uranus and Neptune, which have methane in their upper atmospheres, appear blue-green. A diamond planet with a methane atmosphere would likely show similar coloration. The combination of a crystalline carbon surface and a hydrocarbon atmosphere would create a world utterly unlike anything in our solar system, a place where organic chemistry dominates without biology, where the building blocks of life exist in abundance, but in configurations that never organize into living systems. The temperature regime on such a planet would profoundly affect methane's behavior. At low temperatures, methane can condense into liquid or even freeze into solid ice. On Saturn's moon Titan, the largest moon in the solar system with a substantial atmosphere, methane exists in all 3 phases. The atmosphere is nitrogen-rich with significant methane. Methane clouds form and produce methane rain. Liquid methane collects in lakes and seas on Titan's surface, creating a hydrological cycle analogous to Earth's water cycle, but operating at temperatures around -180 degrees Celsius. A cold diamond planet orbiting far from its star might exhibit similar behavior, with methane weather systems, methane precipitation, and liquid methane accumulating in low-lying regions. But here the diamond surface introduces a strange contradiction. Liquid methane would pool on a surface harder than any substance the liquid could erode. Diamond lake beds and diamond river beds, carved not by the liquid itself but by impact cratering or ancient tectonic activity, would channel methane flows across the landscape. The liquid would be clear and colorless, reflecting the crystalline substrate beneath it, creating bodies of liquid that appear diamond clear in both literal and figurative senses. If the planet orbits closer to its star, temperatures might prevent methane from condensing, keeping the atmosphere gaseous and potentially creating a thick, hazy environment similar to Titan's atmosphere, but without the surface liquids. Photochemistry, driven by ultraviolet light from the star, would break apart methane molecules and recombine them into more complex hydrocarbons: ethane, propane, acetylene, and eventually long-chain polymers that form haze particles. These particles would scatter light, creating a murky orange or brown atmosphere that obscures the surface from external observation. This presents an observational challenge. If the diamond planet has a thick, hazy atmosphere, Webb's infrared observations might not be detecting the surface at all. The diamond signature could be coming from crystalline carbon particles suspended in the atmosphere, diamond dust created by unusual chemical processes in a carbon-rich environment. True surface composition might remain hidden beneath the haze, accessible only through more sophisticated observations or eventually direct exploration. The possibility of diamond dust in the atmosphere is not as far-fetched as it might seem. On Earth, certain industrial processes produce diamond particles from carbon-rich gases. Chemical vapor deposition, a technique used to create synthetic diamonds, works by breaking apart methane molecules in a plasma and allowing carbon atoms to settle onto a substrate where they crystallize into diamond. If similar processes occur naturally in a planet's atmosphere, driven by stellar radiation or electrical discharges analogous to lightning, diamond particles could form and remain suspended in the air. Such an atmosphere would be spectacular to observe from within, if observation were possible. Sunlight filtering through suspended diamond particles would create optical effects unlike anything seen on Earth. Each microscopic diamond would act as a tiny prism, refracting and dispersing light into spectral colors. The sky might shimmer with rainbow glints, a perpetual atmospheric aurora created not by magnetic fields and charged particles, but by the optical properties of airborne crystalline carbon. Clouds, if they formed from condensing hydrocarbons, might be laced with diamond dust, creating formations that sparkle even in dim light. But the most profound implications of the diamond planet discovery may lie not in what it tells us about that specific world, but in what it reveals about the broader population of exoplanets waiting to be discovered. For decades, astronomers assumed that planets would broadly resemble those in our solar system: rocky terrestrial worlds, gas giants, ice giants. Early exoplanet discoveries seem to confirm this expectation, albeit with variations. Hot Jupiters, gas giants orbiting extremely close to their stars, were unexpected, but could be explained within existing planetary formation theories. As observations improved and the exoplanet catalog expanded, more exotic categories emerged. Super-Earths, planets larger than Earth but smaller than Neptune, with no analog in our solar system. Mini-Neptunes, worlds with thick hydrogen atmospheres but rocky cores. Lava planets, tidally locked worlds with one hemisphere perpetually melted by stellar heat. Water worlds, planets covered entirely by deep global oceans. Each new category expanded the taxonomy of planetary types and challenged assumptions about what planets could be. The diamond planet adds carbon worlds to this taxonomy, a category predicted by theory but unconfirmed until now. And if carbon-rich planetary formation is possible, then other exotic chemistries almost certainly produce equally unusual worlds. Silicon carbide planets, where carbon and silicon combine into an incredibly hard ceramic material, might exist in systems with unusual silicon abundance. Corundum planets, where aluminum and oxygen form crystalline structures known on Earth as rubies and sapphires, could form an aluminum-rich nebulae. Iron planets, essentially exposed planetary cores stripped of their rocky mantles by collisions, might orbit in systems with violent early histories. Each of these planetary types would have distinct properties, different geological behaviors, different responses to stellar heating, different atmospheric chemistries. Some might be geologically active despite unusual compositions. Others might be static and unchanging. Some might retain thick atmospheres. Others might be airless and exposed. The diversity is limited only by chemistry and physics, and both allow for a staggering range of outcomes. This diversity has profound implications for the search for life beyond Earth. For years, the search for extraterrestrial life has focused on finding Earth-like planets, rocky worlds in the habitable zone around sun-like stars, with liquid water on the surface and temperate climates. This approach makes sense given that Earth is our only example of a life-bearing world, but it also risks missing life that exists in environments we have not considered. A diamond planet seems like an implausible candidate for life, yet it challenges us to think more broadly. If liquid methane exists on the surface, could life use it as a solvent instead of water? Theoretical biochemistry suggests that methane-based life is not impossible, merely different. Such organisms would operate at extremely low temperatures and would utilize different chemical reactions for metabolism. But the fundamental requirements, a liquid medium, an energy source, and chemical building blocks, could theoretically be met. Even more speculatively, could life exist within the diamond itself? On Earth, microorganisms inhabit solid rock kilometers below the surface, extracting energy from chemical reactions between minerals and slowly metabolizing in environments that seem utterly inhospitable. Diamond's crystalline structure is far more rigid than sedimentary rock, offering little space for organisms, but impurities and fractures might create microenvironments where exotic biochemistry could persist. This remains pure speculation, but the point is that assumptions about habitability must constantly be questioned as our catalog of planetary environments expands. Beyond biology, the diamond planet raises questions about resource utilization in a hypothetical future where humanity or other civilizations achieve interstellar travel. Science fiction often depicts asteroid mining and resource extraction from other planets, but those scenarios typically envision mining metals, water ice, or rare elements. A diamond planet presents a resource that is simultaneously abundant and, by current standards, valuable. If future technology allows interstellar travel, would a diamond planet become a mining target? Or would the sheer abundance of diamond make it economically worthless? This question touches on fundamental economics. Value derives from scarcity relative to demand. On Earth, diamonds are valuable because they are rare and desired for both aesthetic and industrial purposes. But if a single planet contains more diamond than could ever be used even by a spacefaring civilization, scarcity vanishes, and so does value. The diamond planet could paradoxically be both the greatest treasure in the galaxy and utterly worthless, depending on access and demand. However, industrial applications might tell a different story. Diamond is not just decorative. It is an exceptional material for cutting tools, heat sinks, radiation-resistant electronics, and optical components. A civilization with access to unlimited diamond could build technologies impossible with limited supplies. Quantum computers might use diamond substrates for their superior thermal and optical properties. Spacecraft could be armored with diamond plating, resistant to micrometeorite impacts and radiation. Power systems could use diamond heat exchangers, conducted waste heat away from reactors with unmatched efficiency. In this sense, a diamond planet might be less like a gold mine and more like an iron deposit. Iron is common and not particularly valuable per kilogram, but its utility makes it foundational to industrial civilization. Similarly, diamond in vast quantities might become a fundamental industrial material, valuable not for rarity but for its properties and the technologies it enables. A civilization that could access and process material from a diamond planet would have capabilities far beyond those limited to conventional rocky or metallic resources. But all of this remains distant speculation. Humanity has not yet achieved interstellar travel, and the challenges involved make even visiting nearby star systems extraordinarily difficult. The diamond planet Webb observed is 40 light-years away, a distance so vast that it defies intuitive comprehension. Light, traveling at 300,000 kilometers per second, takes 40 years to cover that distance. Our fastest spacecraft move at tiny fractions of light speed and would require tens of thousands of years to reach the same destination. Chemical rockets, ion drives, even hypothetical nuclear propulsion systems all fall far short of what would be needed. This is where theoretical concepts like warp drives, generation ships, or even more speculative ideas like wormholes enter the conversation. None of these technologies currently exist, and some may prove impossible regardless of technological advancement. But the existence of extraordinary worlds like the Diamond Planet provides motivation for considering such technologies seriously. If the universe contains wonders we can observe but not reach, the impulse to develop means of reaching them becomes a powerful driver of innovation. Even without physical travel, the Diamond Planet offers value simply by existing and being observable. Every photon of light Webb captures from that distant world carries information about its composition, temperature, and structure. Spectroscopy reveals the chemical fingerprints embedded in that light. Observations over time track the planet's orbit, measure its mass through gravitational interactions, and detect any changes in brightness or spectrum that might indicate atmospheric weather or surface features. These observations contribute to a growing understanding of planetary systems as complex, dynamic entities rather than static collections of orbiting bodies. Just as Earth's climate system involves interactions between atmosphere, oceans, ice, and biosphere, exoplanetary systems involve interactions between stellar radiation, planetary composition, atmospheric chemistry, and possibly even life. Each planet is an experiment in how matter organizes under specific conditions, and each observation adds data to the vast experiment the universe has been running for billions of years. The Diamond Planet also serves as a reminder of how much remains unknown. Despite decades of astronomical observation and centuries of scientific inquiry, we are still discovering fundamental categories of objects. The first exoplanet around a sun-like star was confirmed only in 1995, less than 30 years ago. Before that, we knew of only 8 planets total, all in our solar system. Now we know of thousands, and estimates suggest billions of planets exist in our galaxy alone. Each one is unique. Each one has a story written in its composition and structure, and we are only beginning to read those stories. Webb represents a leap forward in observational capability, but it is not the end point of astronomical technology. Future telescopes will be larger, more sensitive, capable of detecting fainter signals and analyzing them in greater detail. Ground-based observatories are planning extremely large telescopes with mirrors 30 or even 40 meters in diameter, dwarfing current instruments. Space-based missions beyond Webb are being designed, including concepts for interferometric arrays that combine light from multiple spacecraft to achieve resolution impossible with single telescopes. These future instruments will study the Diamond Planet in greater detail, resolving features on its surface if it has no obscuring atmosphere, mapping temperature variations between day and night sides, detecting any moons or rings and searching for temporal changes that might indicate geological activity or atmospheric phenomena. Each new observation will refine our understanding and raise new questions. This is the nature of science. Answers generate questions, and questions drive new observations. The broader context of this discovery extends beyond astronomy and planetary science into philosophy and human self-understanding. For most of human history, Earth was the only known world. The moon and planets were lights in the sky, mysterious and unreachable. The universe seemed vast but empty of places fundamentally similar to our own. This perspective shaped religious and philosophical thinking, placing humanity and Earth at the conceptual center of existence. The Copernican revolution began changing this view, showing that Earth orbits the Sun rather than vice versa, that our planet is one among several. Later discoveries revealed that the Sun is one star among hundreds of billions in our galaxy, and that our galaxy is one among hundreds of billions in the observable universe. Each step moved humanity farther from any claim to centrality or uniqueness. The discovery of exoplanets, and especially the realization that planets are common rather than rare, continued this trajectory. Now we know not only that other worlds exist, but that they are staggeringly diverse. Some resemble Earth. Others are unlike anything we imagined. Diamond planets, lava worlds, water planets, rogue planets wandering interstellar space without stars. Each discovery emphasizes that Earth is one outcome among countless possibilities. We are not central. We are not typical. We are simply one configuration of matter that happened to arise in one small corner of a vast and varied universe. This perspective can feel diminishing, but it can also be profoundly liberating. If the universe creates worlds as strange as diamond planets, then it is far more interesting and full of possibility than a cosmos containing only familiar Earth-like planets would be. The strangeness itself has value. It stimulates curiosity, drives exploration, and reminds us that reality exceeds imagination. No matter how creative our science fiction, the universe produces realities more exotic than we can easily invent. The diamond planet exists whether we observe it or not, whether we understand it or not, whether we care or not. It orbits its star in accordance with physical laws, its surface glittering in starlight, its interior structured by pressure and temperature, its fate determined by the same forces that govern all matter. It does not exist for us. It does not convey meaning or purpose. It simply is, a concentration of crystallized carbon shaped by gravity and time into a spherical world. Yet we assign it meaning by observing it, naming it, studying it, and trying to understand how it came to be. That act of observation and understanding is fundamentally human. We are the species that looks outward, asks questions, builds instruments to extend our senses, and constructs explanations that make sense of the data those instruments provide. The diamond planet matters because we make it matter, because we recognize its significance and allow it to shape how we see the universe. And so the discovery stands as both a scientific achievement and a cultural moment. The James Webb Space Telescope detected something extraordinary. Scientists analyzed the data, recognized its implications, and shared the finding with the world. Now the knowledge exists, somewhere out there, 40 light-years away. A world made of diamond circles its star, a crystalline anomaly in the cosmic dark. We cannot visit it. We cannot mine it. We cannot meaningfully interact with it except through observation. But we know it exists, and that knowledge changes us, however subtly. It expands what we know is possible. It challenges what we thought we understood. It adds another data point to the grand catalog of cosmic phenomena. And it reminds us once again that the universe is vast beyond comprehension and strange beyond prediction, filled with worlds and wonders we have only begun to discover. The diamond planet will continue orbiting its star long after human civilization has passed into history. It will remain unchanged, indifferent, eternal. But for this brief moment in cosmic time, we have noticed it, and that makes all the difference. If this discovery fascinates you as much as it fascinates scientists around the world, remember that exploration is a shared endeavor. Every observation, every telescope image, every spectrum analyzed brings us closer to understanding the full diversity of worlds the universe contains. The diamond planet is just one example. There are billions more waiting to be found, each one unique, each one offering new insights into how nature works when freed from the constraints we know on Earth. The journey of discovery continues, and we are only at the beginning. A flash of infrared light captured by the most powerful telescope humanity has ever built reveals something that shouldn't exist. A world where the ground beneath your feet isn't rock or ice, but carbon compressed into crystalline perfection. Where mountains rise not from stone, but from the same material that adorns engagement rings and industrial drills. A planet made entirely of diamond, not a metaphor, not an exaggeration. An actual celestial body where the dominant substance is crystallized carbon in its hardest, most brilliant form. The James Webb Space Telescope didn't just find an unusual world, it found something that challenges our understanding of planetary formation, challenges what we thought chemistry could produce on cosmic scales, and forces us to reconsider what kinds of worlds the universe creates when conditions push beyond familiar limits. If you're fascinated by this discovery, subscribe and hit that like button so we can explore this extraordinary find together. To understand why a diamond planet is so remarkable, we first need to appreciate just how strange diamonds are even on Earth. Carbon is one of the most common elements in the universe. It forms the backbone of organic chemistry, builds the structures of life, and appears in stars, nebulae, and planetary atmospheres throughout the cosmos. Yet despite being abundant, carbon rarely appears in its diamond form naturally. On Earth, diamonds form deep underground, roughly 150 kilometers beneath the surface, where pressure reaches extreme levels and temperatures soar above 1,000 degrees Celsius. At these depths, carbon atoms arrange themselves into a rigid three-dimensional lattice structure unlike anything found in softer carbon forms like graphite or coal. This lattice creates exceptional hardness and optical properties that make diamonds both valuable and scientifically fascinating. But even under those brutal conditions, diamonds remain rare. Most carbon on Earth exists in other forms: limestone, organic compounds, atmospheric carbon dioxide, fossil fuels. Diamond formation requires a precise combination of depth, heat, pressure, and time. Even when conditions align perfectly, the process produces only small deposits scattered across specific geological environments. Volcanic eruptions sometimes carry these diamonds upward through structures called kimberlite pipes, delivering them close enough to the surface that mining becomes possible. Without those rare geological accidents, most diamonds would remain forever buried, inaccessible and unknown. This scarcity shapes everything we think we know about diamonds. They are precious because they are rare. They form only under exceptional circumstances. They represent a crystalline anomaly in a universe where carbon prefers softer, more flexible arrangements. So, when astronomers point telescopes toward distant star systems and identify entire worlds where diamond isn't rare but dominant, it forces a complete recalibration of expectations. The universe is not just creating pockets of crystallized carbon, it is building planets from it. The James Webb Space Telescope made this discovery while studying a star system roughly 40 light-years from Earth. The target was not particularly remarkable at first glance. A moderately sized star, slightly cooler than our Sun, orbited by several planets at varying distances. Standard exoplanet territory. Routine observation. But as Webb analyzed the infrared signature of one particular planet, something unusual emerged. The spectral data didn't match any known planetary composition. It wasn't rocky like Earth or gaseous like Jupiter. It wasn't icy like Neptune or metallic like Mercury's core. The light reflected from this world carried a signature that pointed unmistakably toward carbon in a highly ordered crystalline structure. Diamond. At first, the data seemed implausible. Planets are supposed to form from the material available in their birth nebulae: hydrogen, helium, silicates, metals, ices. Carbon exists in those clouds, certainly, but not in concentrations high enough to dominate planetary formation. Yet the infrared spectrum persisted. The more Webb observed, the stronger the evidence became. Thermal emissions, reflectivity patterns, density calculations derived from gravitational interactions all pointed toward the same conclusion. This was not a planet with diamond deposits. This was a planet made of diamond. Understanding how such a world could form requires stepping back to examine planetary birth itself. Planets do not appear fully formed. They coalesce gradually from the swirling disk of gas and dust surrounding young stars. Gravity pulls particles together. Collisions fuse material into larger clumps. Over millions of years, these clumps grow into planetesimals, then protoplanets, and eventually mature worlds. The composition of a planet depends entirely on what material was available during formation and what physical conditions dominated that region of space. In our solar system, the inner planets formed close to the Sun, where temperatures were high enough to vaporize volatile compounds like water and methane. Only materials with high melting points survived: silicate rocks, iron, nickel. This is why Earth, Mars, Venus, and Mercury are rocky worlds with metallic cores. Farther out, beyond the frost line, temperatures dropped low enough for ices to condense. This is where gas giants formed, accumulating massive atmospheres of hydrogen and helium around cores of rock and ice. Each region of the solar system produced planets suited to local conditions. But what if the local conditions were fundamentally different? What if a planetary system formed from a nebula unusually rich in carbon and unusually poor in oxygen? Oxygen normally binds with carbon to create carbon monoxide and carbon dioxide, locking carbon into gaseous compounds. But if oxygen is scarce, carbon remains free. Under the right pressure and temperature conditions, that free carbon can crystallize. Not into graphite, which is soft and layered, but into diamond, which is rigid and three-dimensional. The process that happens rarely and locally on Earth could, under the right cosmic circumstances, happen on planetary scales. This is the scenario astronomers believe created the diamond planet Webb observed. The star system likely formed from a carbon-rich nebula where oxygen concentrations were unusually low. As the protoplanetary disk cooled and material began condensing, carbon dominated the chemistry. Without oxygen to bind it, carbon atoms found each other and began arranging into crystalline lattices. Pressure from gravitational collapse and heat from radioactive decay within the growing planet provided the energy needed to lock those lattices into diamond structures. Over millions of years, layer upon layer of crystallized carbon accumulated until an entire world emerged, glittering and impossibly hard, orbiting its star in silent permanence. The implications of this discovery extend far beyond a single unusual planet. If one carbon-rich world exists, others almost certainly do as well. The universe contains billions of star systems, each formed from nebulae with unique chemical compositions. Some will be oxygen-rich, favoring rocky planets like Earth. Others will be metal-rich, producing dense iron worlds. And some, a rare subset, will be carbon-rich enough to create diamond planets. Webb's discovery suggests these exotic worlds are not just theoretical possibilities. They are real, observable, and waiting to be studied. What would such a planet actually look like? Standing on its surface, assuming you could survive the environmental extremes, the landscape would be both familiar and utterly alien. The ground would be hard beyond anything experienced on Earth. Diamond is the hardest naturally occurring material known, resistant to scratching, compression, and deformation. Walking across this surface would feel like traversing an endless field of industrial abrasive. Mountains would rise in jagged, crystalline peaks, their facets catching and refracting light in ways stone mountains never could. If the planet has an atmosphere, and that remains uncertain, sunlight filtering through it would shatter into spectral rainbows across diamond cliffs and valleys. The optical properties alone would be staggering. Diamond's refractive index, the measure of how much it bends light, is among the highest of any transparent material. Light entering a diamond slows dramatically and changes direction sharply, creating the brilliant sparkle associated with cut gemstones. On a planetary scale, this effect would transform the entire world into a light-scattering prism. Depending on the angle of incoming starlight and the structure of the surface, the planet might shimmer with prismatic colors, casting rainbows across its sky and surface in patterns that shift with orbital position. But beauty aside, the physical properties of a diamond planet raise extraordinary questions about geology, tectonics, and long-term stability. On Earth, geology is driven by heat. Radioactive decay in the planet's interior generates thermal energy. That energy drives convection in the mantle, which powers plate tectonics, which shapes continents, builds mountains, and recycles crust. This dynamic process has operated for billions of years, constantly reshaping Earth's surface and interior. But diamond conducts heat exceptionally well, far better than rock. A diamond planet would not trap heat the way Earth does. Instead, thermal energy would radiate outward rapidly, cooling the interior and potentially freezing geological activity entirely. Without active geology, a diamond planet might be profoundly static. No tectonic plates grinding against each other. No volcanic eruptions releasing gases and building new land. No convective recycling of material between surface and interior. The planet would be geologically dead, its surface locked into whatever configuration it achieved during formation. Ancient impact craters would remain forever, unweathered and unburied. Mountain ranges would stand unchanged for billions of years. The world would be a frozen snapshot of its early history, preserved in crystalline permanence. This raises another challenge. Atmosphere. On Earth, volcanic outgassing continuously replenishes atmospheric gases. Without active volcanism, a diamond planet would struggle to maintain a substantial atmosphere over geological timescales. Any atmosphere present during formation would gradually erode, stripped away by stellar wind and lost to space. The planet might become airless, a glittering vacuum-exposed sphere with no weather, no wind, and no protection from cosmic radiation. Alternatively, if the planet formed with a thick primordial atmosphere and lacks active geological recycling, that atmosphere might persist unchanged for billions of years, a stagnant envelope of ancient gases surrounding a motionless world. Temperature adds another layer of complexity. Diamond's thermal conductivity means the planet's surface temperature would closely match its equilibrium temperature, the balance between energy received from its star and energy radiated back into space. Unlike Earth, where atmospheric greenhouse effects and ocean currents redistribute heat, a diamond planet would have minimal temperature moderation. The day side, facing the star, would bake under direct radiation. The night side, turned away, would freeze. The terminator region, the boundary between day and night, might be the only zone where temperatures remain moderate enough for certain chemical processes to occur. And then there is the question of what else might be present. A planet made entirely of diamond is an extreme idealization. In reality, even a carbon-dominated world would contain impurities. Trace amounts of silicon, iron, nitrogen, hydrogen, and other elements would inevitably mix into the crystalline structure during formation. These impurities would affect the planet's properties in subtle but important ways. Nitrogen impurities, for instance, create yellow and brown tints in Earth diamonds. Iron can produce blue or green hues. On a planetary scale, such impurities might create vast color zones across the surface, regions where the crystalline lattice contains different trace elements and reflects light differently. Some of these impurities might even create localized regions where diamond transitions into other carbon forms. Graphite, for example, is chemically identical to diamond, but arranged in layered sheets rather than three-dimensional lattices. Under lower pressure or different thermal conditions, carbon might crystallize as graphite instead. A diamond planet could theoretically contain graphite deposits, regions where the carbon adopted a softer structure. These zones would be geologically distinct, perhaps forming valleys or plains between diamond highlands, creating a variegated landscape of crystalline contrasts. The discovery also forces us to reconsider resource distribution across the universe. On Earth, diamonds are rare and valuable precisely because they form only under exceptional conditions in limited quantities. But on a diamond planet, the material we consider precious becomes the most common substance. The entire planet, from surface to core, would be composed of material that on Earth costs thousands of dollars per carat. The economic implications are almost absurd. If humanity ever developed interstellar travel and reached such a world, the concept of diamond value would collapse entirely. Scarcity would vanish. The market would dissolve. What we treasure would become as common as sand. Of course, reaching such a planet remains far beyond current capabilities. 40 light-years is an incomprehensible distance in practical terms. Even traveling at the speed of light, which remains impossible for massive objects, the journey would take 4 decades. With current propulsion technology, the trip would require tens of thousands of years. The diamond planet is observable, analyzable through telescopes, but entirely inaccessible. It exists as a scientific curiosity and a philosophical provocation, not as a destination or resource. Yet the discovery itself carries profound value. It expands the catalog of planetary types, adding a category that theoretical models predicted but observations had never confirmed. It demonstrates that the universe creates worlds far stranger than the familiar rocky and gaseous planets dominating our own solar system. It shows that chemistry, given the right starting conditions, can produce outcomes that feel exotic and improbable, but are entirely consistent with physical laws. A diamond planet is unusual, but it is not impossible, and that distinction matters. The James Webb Space Telescope's ability to make such a discovery highlights just how far observational astronomy has advanced. Decades ago, detecting exoplanets at all was considered extraordinarily difficult. Planets do not emit their own light. They are tiny compared to their stars. They are separated from us by vast distances. Early exoplanet discoveries relied on indirect methods, measuring the wobble in a star's position caused by an orbiting planet's gravity or detecting the dimming of starlight as a planet transited across the star's disk. These methods revealed that exoplanets exist and that they are common, but they provided limited information about planetary composition. Webb changes that equation. Its infrared sensitivity allows it to analyze the light reflected and emitted by exoplanets directly. By studying the wavelengths present in that light, astronomers can identify the chemical signatures of planetary atmospheres and surfaces. Different molecules absorb and emit light at characteristic wavelengths, creating spectral fingerprints that reveal composition. This is how Webb identified the diamond planet, by detecting the specific infrared signature of crystallized carbon in the light reflected from the planet's surface. This technique, known as spectroscopy, will only improve as technology advances. Future telescopes, even more sensitive than Webb, will be able to study smaller planets, fainter signals, and more distant systems. The catalog of known exoplanets will expand from thousands to millions, and within that expanding catalog, more exotic worlds will emerge. Diamond planets will likely prove to be just one category among many. There may be planets with surfaces of silicon carbide, harder even than diamond. Worlds where the crust is metallic hydrogen, compressed into solid form by extreme pressure. Planets with atmospheres of vaporized rock, where clouds are made of molten silicates and rain falls as liquid iron. Each discovery reshapes our understanding of what planets can be. Earth, once considered the standard planetary model, now appears as one variation among countless possibilities. The universe does not favor familiarity. It explores every available configuration, every chemical pathway, every physical extreme. Some of those configurations produce worlds like ours, temperate and stable, capable of hosting life. Others produce diamond planets, carbon worlds, lava oceans, rogue ice balls wandering interstellar space without stars. The diversity is staggering, and we are only beginning to catalog it. The diamond planet also raises questions about the potential for life. At first glance, such a world seems profoundly hostile to biology. Life as we understand it requires liquid water, organic chemistry, and energy sources that drive metabolic reactions. A diamond planet, geologically inert and possibly airless, offers none of these. The surface would be sterile, exposed to radiation and subjected to extreme temperature swings. No liquid water, no organic molecules, no obvious energy gradients to exploit. Life, at least life resembling anything found on Earth, seems impossible. But biology is creative in ways that constantly surprise scientists. Earth hosts extremophiles, organisms that thrive in environments once considered uninhabitable. Boiling hydrothermal vents, acidic lakes, deep underground rock formations, frozen Antarctic ice. Life adapts, it exploits niches, it finds pathways to survival that seem improbable until discovered. Could life exist on a diamond planet? Not on the surface, certainly, but perhaps in subsurface environments, if any exist. If the planet's interior retains heat, if liquid water exists in deep underground reservoirs, if organic compounds accumulated during formation, then microbial ecosystems might persist in isolated pockets far beneath the crystalline crust. This remains speculative, of course. No evidence suggests life on the diamond planet Webb observed, but the question itself is worth asking because it forces scientists to think beyond familiar paradigms. Life might not require Earth-like conditions. It might not require liquid water in all cases. Silicon-based biochemistry, while hypothetical, is not ruled out by chemistry. Organisms might metabolize in ways we have not yet imagined, using energy sources we do not recognize, building structures from materials we consider inert. The universe is vast and creative. Assuming we understand all possible forms of life is almost certainly premature. Even without life, the diamond planet offers scientific value that extends into multiple disciplines. Geochemists can study how carbon-rich planetary systems evolve and what conditions favor diamond formation over other carbon structures. Astrophysicists can refine models of planetary formation, incorporating carbon-dominated scenarios into broader theories of how star systems develop. Material scientists might one day analyze diamond samples from such worlds, studying crystalline structures formed under conditions impossible to replicate in laboratories. Each layer of investigation peels back another aspect of how the universe operates at scales both vast and detailed. The discovery also connects to deeper questions about cosmic abundance and element distribution. Carbon, nitrogen, oxygen, silicon, iron. These elements form in stars through nuclear fusion and are scattered across space when stars die. Supernovae and stellar winds seed the interstellar medium with the raw materials for future star systems. The composition of each new nebula depends on which stars contributed material and what nuclear processes they underwent before death. A nebula enriched by carbon-rich supernovae would naturally produce carbon-rich planets. One enriched by oxygen-rich stellar winds would favor silicate worlds. The periodic table in this sense is not just a chart of elements, it is a blueprint for planetary diversity. Understanding this connection helps astronomers predict what kinds of planets should exist around different types of stars. Stars with high metallicity, meaning they contain more heavy elements than pure hydrogen and helium, are more likely to host rocky planets. Stars with unusual carbon-to-oxygen ratios are candidates for hosting carbon worlds. By analyzing stellar spectra, astronomers can infer what kinds of planets might orbit those stars even before detecting the planets themselves. The Diamond Planet fits this pattern. Its star shows a carbon-rich signature consistent with the idea that the planetary system formed from carbon-enriched material. This predictive power transforms exoplanet science from a purely observational field into one that combines observation with theory. Instead of simply cataloging planets as they are discovered, astronomers can now hypothesize about what should exist and then search for it. The Diamond Planet was not entirely unexpected. Theoretical models had suggested carbon-rich worlds were possible. Webb's observation confirmed the prediction. Future discoveries will likely follow the same pattern. Theory suggests a planetary type. Technology improves to the point where detection becomes possible, and observation validates or refutes the hypothesis. But amid all the scientific rigor and theoretical modeling, there remains something deeply human about this discovery. A planet made of diamond captures the imagination in ways that a standard rocky world does not. It feels like something from mythology or fantasy, a treasure beyond reach, a world that glitters in the darkness of space. That emotional resonance matters. It reminds us why we explore, why we build telescopes, why we dedicate resources to understanding distant worlds we will never visit. Because the universe is strange and beautiful and endlessly surprising. Because discovery itself, the act of learning something new about reality, carries intrinsic value. The Diamond Planet will never be mined. It will never be colonized. It will never serve as a resource or a destination. But it exists, and knowing it exists changes how we see the cosmos. It expands the boundaries of the possible. It challenges assumptions. It forces us to acknowledge that our experience of planets, Earth, Mars, Venus, the gas giants, represents an infinitesimally small sample of what the universe creates. Out there, beyond our solar system, beyond our immediate neighborhood, are worlds we cannot yet imagine, and some we can barely believe, even after detecting them. This is what makes discoveries like the Diamond Planet so significant. They are not just data points in a catalog. They are windows into the vastness of cosmic possibility. They are reminders that the universe does not conform to our expectations or our limitations. It simply is, creating and destroying, building and reshaping, following physical laws that allow for outcomes ranging from the familiar to the fantastical. Our task as observers and thinkers is to keep looking, keep questioning, and keep revising our understanding as evidence accumulates. The James Webb Space Telescope will continue observing. It will study more exoplanets, more star systems, more distant galaxies. Some of those observations will confirm existing theories. Others will overturn them. And occasionally, Webb will find something like the Diamond Planet, something that sits at the edge of theoretical prediction and observational capability. Something that feels almost too strange to be real, but is nonetheless undeniably present in the data. Future missions will build on Webb's findings. Ground-based telescopes will conduct follow-up observations. Space-based instruments with even greater sensitivity will launch in the coming decades. The catalog of known exoplanets will grow from thousands to hundreds of thousands. And within that growing catalog, the Diamond Planet will remain a landmark discovery. The first confirmed world where carbon crystallized on planetary scales. The first place where the universe demonstrated that what we consider precious can, under the right conditions, become the foundation of an entire world. For now, the diamond planet orbits its star in silence, 40 light-years away, indifferent to our fascination. It does not know it has been observed. It does not care that its existence challenges our assumptions. It simply is. A glittering anomaly in the cosmic dark, a reminder that reality is stranger and more wonderful than we often allow ourselves to believe. And as long as we continue to look outward, to point our instruments toward distant stars and analyze the light they reflect, we will keep finding worlds like this. Worlds that defy expectation. Worlds that expand understanding. Worlds that prove, again and again, that the universe's capacity for creativity far exceeds our capacity to predict it.